Hello, I'm Jenny Grosslight with Keysight Technologies. This video offers a guided tour of DDR Setup Assistant using a DDR4 example. DDR Setup Assistant is the only supported method for tuning your logic analyzer to capture DDR or LPDDR memory traffic. To get started, download and install the latest version of the software for the logic analyzer and for the B4661A memory analysis software. To properly install the software, you must have full administrator privilege on the host machine. Install the main logic analyzer software first, then install the B4661A software. You will also need to install any B4661A licensed options for the DDR or LPDDR technology of interest. Instructions for installing the license will come in an email when you purchase the license. Once you have your software loaded, run the DDR Setup Assistant. This is the fastest way to get the most accurate measurements. Double-click on the DDR Setup Assistant. This will start the logic analyzer service, and it will open up a session for you. The default is just seeing the logic analyzer waveform and a listing. As you go through the Setup Assistant, it's going to set up quite a bit of detailed information for you. You need to step through and answer the questions, basically. Here, we're going to be demoing a DDR4 system. The setup is going to be very similar for any of these memory technologies or interposer solutions. The general process is similar. The actual connections are different, and some of the software decode is obviously different. Here we're using a DDR4 BGA interposer on a by 8 DRAM with the W4643A interposer, and we are prepared and connected to go to speeds above 2.5 gigatransfers per second. Once we're finished, this step is complete. Then you check the software. This will check to make sure that you've licensed the applications that are needed, and also tells you others that you might have licensed. I generally load the standard configuration and load the configuration file. This is important. When you do this, it's going to load the default configuration for the specific interposer that you have selected. This is critical because the exact mapping of the signals into the logic analyzer corresponds to the exact interposer and cabling that all go together as part of the solution. Once that's loaded, let's look at the overview and see what got loaded here. You notice when I try to go to the logic analyzer, the panel's locked. That's Setup Assistant has it locked. Let's go to the overview and see the configuration is loaded. That gives us the probe connections and shows us that it's set up the logic analyzer to be a DDR4 module, has the decoder ready, going into a listing. There's a waveform set up, and the memory analysis is set up. The configuration will have all of the signals mapped for the specific interposer that I selected. I always am careful in this view to cancel out of it. I don't want to accidentally go in and change a bit. Now, if we go back to Setup Assistant and step complete, we loaded the configuration. Now, under hardware setup help, if you actually go in the help, it'll be a Word document to read. But let's go through what it would tell you to do. We go back into the overview, cancel the lock. Go back in and open the properties of the probe connection. Here, it's going to tell you that off of the W4643A, you have actually two cables connected. And in the user guide of the W4643A, there'll be an illustration showing you which of these cables to hook up to which side of the interposer. The U4209A pod A and B, and a U4208A pod A and B. And then they each connect to one of the inputs into the logic analyzer. If you're curious about what's on either one of those pods, you can view and edit and see the exact signals that are coming in. So the configuration is loaded for you. You need to make sure that you're connecting exactly how it shows you in the probe connections. Going back into Setup Assistant, that step's complete. The first thing to do is to find the initial thresholds and set that for all of the signal. This is done automatically by the logic analyzer software looking for the middle point of the swing of the signals. You can do a little sanity check by saying, for the given technology I'm on, does the value, in this case, 582 millivolts for DDR4 make sense? And yes, it does. That would be a good point for the middle of the swing. So that step's complete. Now, in the sample positions of the clock and chip select, depending on the technology you're on and the bus and the interposer you've got, you may have more clock enables that you've got to choose from. DDR4, you might add a command latency in there or might check the gear down. In this particular demo, we're not using those, so we don't check them. And then we have Setup Assistant find the sample positions for the clock and the chip select. It takes it just moments and it's complete. And it does tell us that it thinks we should check the CKE, and we'll do that. But it found the sample position for the clock. Let's find the sample position, step complete there, for the chip select first, because we happen to know for this system, CKE, when it's running a memory test, which it is right now, it's always active. Here we'll find the sample positions of the command and address. And notice it gives you warnings that it didn't find an I for address 13, no valid I's for 17, and none found for ODT. And that could be fine. 17 is oftentimes not used. 13 might not be being used much for this particular test. Well, let's go back now and verify the command and address setting. Now, the tool is doing all of this work. There's things that may not be obvious, but that setting of the thresholds, the setting of all of the sample positions, getting all of the labels right for you, this is a big deal. So using the default configurations and running through Setup Assistant will save you time and give you the most value. Now, to check the sample positions, we go into the sampling tab, and that's this icon, and open up the iScan window. Here we can expand this, and we see that we've got the first I to the left of 0 has been selected. Now we can enlarge this so that we can see it better by going into the edit and then under advanced. Instead of scanning the default range, we can change it to be -2 nanoseconds to 2 nanoseconds, which will make that a little bigger area. And then one thing we see is that CKE just didn't really transition, but the clock, we're seeing a nice clean clock, and we always select the first I to the left of 0. Almost always, most of the applications. First I to the left of 0 for the clock. Then chip select also has a nice clean I. And again, we could change that range to be the -2 to +2. And command and address, nice clean I's, except for the signals that it didn't find an I, which probably means that ODT was always the same value. And when we open up address, we see all nice clean I's, except there just wasn't any transitions on address 13, 17, and ODT. But these are all good. If 13 does transition, it should be in the same spot as the other address signals. So we're good to go on that one. It's also not a bad idea to lock with these little quick buttons here to go ahead and lock your sample positions so you don't accidentally get something to change. We didn't do the data yet, so we'll click OK here. OK again, and go back into Setup Assistant and say steps complete. If you know your read and write latency, then you can input it here. If you don't know your actual system latency, then you can take a quick trace. Go into the waveform. Again, we have to cancel the lock. We go into the waveform, and the default trigger will be set up for a read or a write. And we click Run, take a trace. And what we're looking for is an area where there's been relatively little activity, so no chip selects happening for a while. If we zoom in on this area, what we're going to see is that when the chip selects start, we see an activate, and then a read here. As we scroll down now to the timing zoom, here we can just put the signals of interest actually, which is going to be the clock, the command, and the DQS. Doesn't really matter in timing zoom whether we're looking at read or write DQS because they're actually the same signal. Timing zoom, it's a small window, sampled at 12 gigahertz around the trigger point. And here, instead of being, let's change the base into symbol. What we're looking for now is when chip select is low, we want to put a marker here, place marker 1. We're going to put it here on the first time that chip selects low, rising edge of the clock during a read. Now, marker 2, if I just grab it and move it over, where I want to put it is on the first rising edge. Here's the preamble, the DQS goes low and then starts transitioning to, we go on that first rising edge, and on the measurement, we do a new sample interval measurement to let that be M1 to M2 on CK0. And that tells us that there's 15 clocks between those 2 points, those 2 markers. So our read latency will be 15. Now, if I reduce this and look for another spot where what I'm looking for is an area where I came out of some no-ops and then started traffic so that I know I'm getting the beginning of a burst when I'm looking at data. Now here we had the transitioning of reads to writes. So we should be seeing it transition here. Let's grab M2 and we're going to go to that rising edge and we'll grab M1 and the rising edge of CK during write. So this in clocks is 14. That means that our write latency will be 14. Like I said, if you already knew that 15 and 14 was your system latency, then you would use that. But this way you can figure it out if you don't already know it by using the timing zoom. Now we go back to Setup Assistant, put in the 15 and 14 on the latencies, apply it. And if you went into the help document there, latency help, it would have told you, given you a Word document that will show you the steps that we just went through. That's the steps complete. Now, that step, just put those values into the decoder, and it also will, the compliance tools will use the values that were sent in there. So that step is doing a lot of work for you so that you don't have to go back in and remember everywhere to insert those values. We want to find the ideal threshold on these. First, we find the read sample positions, and I'll go ahead and pause and come back when it's done. It'll just take it a couple minutes, and then we'll do the writes once we finish the reads. Okay, we're done with the read sample positions. Next, we'll do the write, and then we'll go look at them. This is not the fine settings, but it's the initial settings. Now, DDR Setup Assistant has finished finding the read and write sample positions. We're going to go back and check on this. Typically, this step is all you'll need for speeds under 2,400 megatransfers per second. You start going, particularly anything over 3,200, then we'll have an advanced session on how to do full eye scan so that you get the absolute best sample position. In the eye finder mode, where this is all at the ideal threshold. And now what are we looking at here in the data, read data? Let's go ahead and get it to go into advanced and go -2 to +4. That's really where all of the signals were doing anything of interest. And let's think about what we're looking at here. Now on the strobe, we'd actually probably want to be in the second eye if we were worried about the sample position in time. But for the strobes, we're really not. This is a state measurement setup, and the strobes are going to look like a flat line in state mode since they're being sampled once per clock cycle. But they're very handy for timing zoom. You want to make sure that the threshold's right, and you can see that you've got a preamble and then the 8 samples. This is read, so the read strobes are straddling the eyes of the read data. Because we have the configuration that enables us to capture data rates over 2.5 gigatransfers per second, the logic analyzer is sampling once per every clock edge, and that means that we have made data read rising and data read falling labels for all of the signals. So if you expand each of these labels, you'll see that the whole byte lane is there. But the rising edge is the first eye, and then the falling edge we're setting up to be sampled in the second eye, because they're going to actually sample at the same time, and the software is going to stitch the data capture together for us in the decoder, in the listing and in the transaction decoder for us. Might as well lock those sample positions. The fact that we have open eyes at the ideal threshold for all 8 samples in a burst means these are going to overlay nicely, and we'll have accurate data capture from this system. Now looking at the right eyes, let's again go back in and go to advanced, -2 to +4, get a little more expanded there. You can even re-render here. And again, we've got the right, the rising and the falling, but here we need to change this. Again, I really don't need to change the sample that the DQS is sampled in because it's not going to matter. But we want the eye that it's in to be the rising in the first eye in this view and the falling in the second eye. Now, each of these should be in the center of its suggested eye. We can go ahead and right click on it and set sample only to suggested or average, but suggested it'll go to the center of that eye. Same thing for the falling. Set sample position only to suggested. So first eye, second eye. First eye for the rising, second eye for the falling. And the way that this worked, this is called signal trace mode, and it was set up for you in the scan threshold. When DDR Setup Assistant ran, it ran in the signal trace mode, view the beginning, and it do not store back-to-back memory bursts. It changed it at the end, so. But this, and from your selections as you were going through Setup Assistant, it went through these scan windows and set them up according to which chip selects are set up in the system and getting the correct latency in the window. So, like I said, there's a lot going on in Setup Assistant for you. But what that scanning the signal trace mode does then, and no back-to-backs, is it's showing you where the strobe is relative to the data. And in writes, it's only writes, and reads, it's only reads. So we're doing the read-write separation here. 0 is the reference clock edge. So you're seeing in this case, we have all 8 are captured on screen. Now, as you go faster, more gets captured on screen in this time. But if you're going slower, you may not see the entire burst on screen at one time. So now we're ready to capture accurate measurements on this system. Look for the video on advanced eye scan where we will go into manually changing to get the full eye scans. Remember to lock your sample positions so that you don't lose them. We can click OK, OK, and then take a trace. And now when we go into the data analysis, let me compute, or into the listing, you're going to see the data associated with each read and write, and you've set up to capture accurate commands and data. To double check your command settings, you can use your post-process compliance tool, go into Tools, External App, Post-process Compliance tool, open that up. While it's opening up, I'll show you the memory analysis view. So we go into Setup, DDR4, the DDR4 module, select tests, and down at the bottom, the last 3 tests are protocol violations. So it doesn't really matter what speed you're going at. These violations, if they happen, it's either a very bad defect in the memory controller or your setup's not right. So we'll go ahead and run once, and that's a quick check to make sure that your settings are correct. We passed. So that's a quick sanity check to see that it actually passed. We can close out our video.